Okay. So then, yeah, let's officially start the session. I see people are still logging in. So I will start with a quick welcome note. So welcome everybody to this iteration of the AI Center Colloquium. We are honored and excited to have as guest today Professor Zeynep Akata from University of Tübingen. And this is a bit of a special visit because Zeynep actually did her studies in media informatics in Bonn and Aachen. So she's now coming back. And in between, she did her PhD at INRIA Rhône-Alpes with Cordelia Schmidt, finishing in 2014. Then she did a postdoc at MPI in Saarbrücken with Bernd Schiele and at the University of Berkeley with Trevor Darrell. After that, she started on an assistant professor position at University of Amsterdam with Max Welling in 2017 through 2019, before she got called on to a professor position in computer science at University of Tübingen, where she still is now, and currently, yeah, further extending her group there. Zeynep has, over the years, gotten an impressive number of awards. She has a Lise Meitner Award for Excellent Women in Computer Science in 2014, and a Werner von Siemens Ring Young Scientist Honor in 2019. In addition, she has received an ERC starting grant also in 2019, and a DHGM Pattern Recognition Award in 2021. So this is very good very good opportunity to extend the prominent speaker list for our AI Center Colloquium. We're very honored to have you here, and we're very much looking forward to your talk. The talk will be on one of the main research directions that you're currently pursuing, namely on explainable AI. So thank you very much for coming, and I'll hand over to you.
Thank you very much for the introduction and also for the invitation. It's my pleasure to be here. And so I'm going to talk about mainly two research directions, both related to explainability. One of them zero-shot learning, and then explainable AI. So the outline of my talk is as follows. First, I will start with how we do visual recognition with minimal supervision. And this requires some form of side information. I will talk about attributes and language for that. And then I will move towards generative models and how we discuss about how we generate textual and visual explanations for visual recognition. And then I will summarize and talk about some future directions. Let's start with visual recognition with minimal supervision. When we look at the data distribution in large-scale data sets like ImageNet, for example, we see that it has a very long-tailed structure. We can see that there are some classes that are very highly populated, and these usually represent objects that we see very frequently around us. So we can take images of them and we can name them very easily. But most of the classes in these data sets are very sparsely populated. And so, for example, in ImageNet, there are only 3 images of this class. It is called Spanish firefly. And because this object is very rarely found in the nature, and it's very difficult to, or we need experts to annotate them, it's a very costly process. So my research focuses on the tail of this distribution. When we don't have access to class labels, or we may not know them, we can still use some intermediate representations. And one of this, an example to that is attributes. Attributes are visually discriminative properties of objects, like black and white, has tail, lives on land, is small. And so we would like to build vectorial representations of the classes that are represented by these attributes. So attributes are typically annotated on a class level, so we don't need, the annotators don't need to look at every image. This has, it's a bit of a noisy process because sometimes the entirety of the object may not be present in the image, but this is an noise that the model has to learn to adapt to. Anyway, so we would like to build vectorial representations, and we see that some of these attributes are common for these two example classes. So the vector will have the value 1. Some of these attributes are specific to one class. So in this case, zebra will have the values 1 and whale will have the values 0. And then some of these attributes are relative to each other. So we can also have values between 0 and 1. So after we build such a representation, now we can tackle tasks like zero-shot learning through multimodal embeddings. So this is a framework that is quite simple, but still very effective. We embed images in an image feature space, and this space is learned with a deep neural network. And this space could be frozen or fine-tuned using images of training classes. And then we embed labels in the class attribute space the way I described before. These attributes are given by annotators and annotated on a class level. And then we need to learn a compatibility between these two spaces. This space is typically frozen, such that the images that belong to the same class get projected onto the same location or the close by locations, and also nearby to the attribute vector of that class and far away from all the other classes. After we learn this W parameters of this projection, we using images of seen classes, we can, at test time, we may receive images of previously seen classes or unseen classes, and all we have to do is to embed them into the image feature space and project them onto the class attribute space and see how far the ground truth, one of the ground truth class attribute vector is, and the closest one, the label of the closest one is the label of the predicted label of that particular image. So there are many benchmark data sets for zero-shot learning, and two of the most widely used ones is Animals with Attributes and Caltech Birds dataset. For the first one, we have 50 classes, and 40 of these classes are used for training. The images of 40 classes are used for training and 10 for test. We have 85 attributes. And then the Birds dataset is much more fine-grained. We have 200 classes of different types of birds, and we use 150 classes for training and 50 for test. And we need many more attributes because these objects are visually very similar to each other. So distinguishing them require more attributes. So for the birds dataset, first of all, we measure accuracy. And the accuracy is the number of correctly classified samples in a class divided by the total number of samples in a class. We sum it up for all the classes, and we divide it by the number of classes, because if these data sets are imbalanced, then we don't want to bias the predictions towards highly populated classes. And we do that for, at test time, I mentioned we could have images from unseen classes or seen classes. We calculate the accuracy separately in both cases. And then we take the harmonic mean, because we would like the model to predict the labels correctly, both for seen and unseen classes. So in this table, I show in the first line the results with a classical ResNet model trained with softmax classifiers, and because the vocabulary is restricted to seen classes only, we can make predictions only on seen classes. And then this multimodal embeddings framework with attributes gives us these results. So the unseen class accuracy is positive, but not a very large number. The seen class accuracy drops quite significantly, but in the end we have a positive number for the harmonic mean. So there are a couple of challenges in this framework or in this task. One, there is a very big difference between the unseen and seen class accuracy. So the classifiers are biased towards seen classes. Then we need some form of side information, and attributes could be costly in case of many fine-grained data sets. We need to collect annotations for them. And the resulting accuracy, the harmonic mean, is quite low. So there are these three challenges we would like to tackle. For one of the challenges where I mentioned we need attributes, we could eliminate them, eliminate the necessity of annotating attributes by asking people, novice users, non-expert users, to look at images without knowing the label of that image. They could tell us what properties they see in these images. This is what we did in this paper, where we asked people to look at the images of birds and flowers, and we asked them to only focus on the object and not the background, or not talk about the activity the object might be doing. We asked them to talk about at least 3 properties and use at least 10 words. And they came up with quite descriptive sentences, which also turned out to be quite class specific. So if we want to use these sentences in a multimodal embedding framework, we need to find a way to extract or convert them to vectors. There are many different ways, of course, but in this paper we used a simple technique where we took every letter in the sentence, we converted it into a binary one-hot vector depending on the position of the letter in the alphabet. That position of the vector will be 1, the rest will be zeros, and the sentence then becomes a matrix of zeros and ones on which we can do convolutions. So we have a convolutional network, and then on top of it we have a recurrent neural network that models in an abstract way the history information, the sequence information, and the hidden unit activations of this RNN is going to give us a vector, and that would be the vector that corresponds to this sentence. And if we want to have a sentence, have a vector for every class rather than every sentence, we just take the average of the average encodings of the sentences that belongs to the same class. There must be many other ways to do this in a better way, but this approximate solution already gave us much better results than attributes actually. But I want to talk about something maybe a bit more interesting. So how can we use generative models as a data augmentation mechanism if we have access to some form of side information? So we use again a generator and a discriminator network that takes in addition to the noise, as it is done in vanilla GANs, we take the encoding of the sentence or the class, and we concatenate it to the noise, and then there is upsampling until a noisy image is generated. And then in the discriminator, we have, it's a conditional discriminator, so it needs to learn whether the image is real or fake, but also if the image content fits with the sentence content. So it is able to do that because we feed every once in a while a real image with its corresponding sentence. And then if we want to do zero-shot learning now, we need to train this model using images, real images of scene classes and real sentences of scene classes. And then after we train it, we after either the model converged or reached a certain number of steps, then we stop training and we freeze the generator, and then we can feed any sentence here. And these sentences could be from unseen classes. Then with the help of that, we can generate noisy images or as realistic images as possible of unseen classes, and use those images, add those images into the training set, and train a softmax classifier without the multimodal embeddings. So language gives us the flexibility to generate as many images as we like. So in this example, I show the image that is generated with the sentence bluebird with black beak, and this image is generated with the sentence red bird with black beak, and these images were generated with the sentences that are in the interpolations in between these two sentences. So they don't necessarily correspond to a semantic meaning, but we can see that if we have two sentences in an embedding space, we can generate any number of images that we want in between these two sentences. So this was the starting point with the multimodal embeddings framework. And then when we generate images and add them to the training set, these are the results that we get. The unseen class accuracy doesn't really improve much. The seen class accuracy drops significantly. So this leads to reduced performance in the final result. So this is not better than having no images, actually. So we thought, instead of generating an image, the pixel values, which is going to be noisy, and extracting features from them, which is what we need for doing classification, instead we can take the sentences and instead of real images, we could use real features, and we try to map the sentence encoding to the image encoding, which doesn't require a convolutional network in the generator and the discriminator side. Simple MLPs do work. And also this leads to more stability in training of the GAN. So we use the exact same fundamental idea of data augmentation using GANs, but instead of using real images, we use real features as the real samples. So with generated images, our results were like this, and with generated features, the results improve significantly. And this is mainly because the unseen class accuracy improves. So there are many other generative models that we can use. One other one is VAEs, variational autoencoders, where so we can take, again, it operates in the feature level. We take an image, extract features from them, and then we have an encoder decoder framework where these two networks are trying to reconstruct the feature, the real feature. And on the other side, this is a multimodal embedding framework. So we have an attributes or sentences, and with that we can design another VAE. At the moment, these two VAEs don't communicate. So to make them communicate, we introduce two additional losses, where the latent embedding of this VAE and this one should be aligned as much as possible. So this distribution alignment ensures that. And then we have a cross alignment objective that ensures that the latent embedding of that is learned from the image features should be enough to reconstruct features of classes, the class embeddings. And vice versa, the features, the latent embeddings learned with class features should be enough to reconstruct the image features. And after we do that, we don't need to feed this model in an image feature or a class feature and then reconstruct it and use that in the training process. But instead, we can just sample from this distribution, and which leads to much lower dimensional features. Of course, we train this model using only images of seen classes, and at test time, we don't have access to images. So, sorry, we don't have access to, not necessarily the class embeddings. So we feed an image, the image to be tested, and then this sample from this VAE. and add that to the training set. Okay, and if we do that, then the results further improve. Maybe the next more natural step would be to combine the two generative models. We have a conditional VAE with which we use class embeddings of scene classes to reconstruct the features of scene classes. And then it has a shared generator, or the decoder of the VAE is shared as the generator of the GAN, where we use a noise vector and the class embedding of scene classes to generate features of scene classes. And this discriminator needs to differentiate between features of scene classes, the real features and fake features of scene classes, and also the reconstructed features of scene classes. And at test time, we feed the unseen class vector here to get to generate the features of unseen classes, and this is what we evaluate. This further improves results. Yeah, so this shows that the data using generative models as a data augmentation mechanism can lead to significant improvements for the zero-shot learning task. And doing this on a fine-grained data set like this BIRDS data set is very kind of challenging, but it still works. But on the conditioned on the fact that the vectors or these site information needs to be class specific and discriminative. If we use, for example, word-to-vec representations of the classes, then it doesn't work. So the class embeddings, the space of classes needs to be well separable. So I talked about attributes earlier, and there are some problems with attributes. Besides them being costly for fine-grained data sets, there are also issues like for some classes, these two attributes may occur always together. And in fact, in the entire training set, always these two attributes may occur together. So there are incidental correlations between attributes, and the model learns these attributes as one attribute, and doesn't necessarily know the meaning of these two separate attributes. And if at test time we receive an image that requires attributes to be decorrelated, then the model fails in these classes. So to alleviate this problem, we thought the attributes could be grouped according to body parts. We manually grouped them because for this data set, the attributes are already written as according to their body parts. So these attribute names were given. We just clustered them together based on the body part. And then instead of learning an encoding of the entire class attribute vector, we learn prototypes, attribute prototypes that corresponds to each of these groups that we had made. And this helps disentangle these attribute encodings. So after we learn these prototypes, we can actually project them onto the images, and they will all lead to some values on the image, and the peak value of that attention map could be used as the value of the attribute. And then we can check if the value of the predicted attribute is close to the ground truth attribute, and if not, this loss could be backpropagated all through the network. So improving the locality of attributes improves results in the zero-shot learning setting, which I will show in the next slide. But visually, doing this also leads to improvements. So this is the prototype network. and we can see that the location of the body parts are, or the body parts are localized correctly. Whereas a model that doesn't do this, focus on the locality of the attributes, sometimes learns the same location for two different body parts. And we also see that qualitatively, for the same attribute, in this case, I'm showing on 3 different classes, where the attribute stripes occurs as the positive attribute for these 2 classes. The attribute is localized correctly. In some cases, for example, rat or killer whale doesn't really contain this attribute, but for these images, the model has detected stripes, and this is because there are stripes-like structures in the image, and this may indicate that the model may have learned the meaning of this attribute. So this multimodal embeddings framework gave us results like this in the very beginning, and with using these attribute prototypes already improves results significantly. I showed results earlier with generated features, and using normal attributes and generated features using those attributes, versus learning with attribute prototypes and the generated features, that leads to slight improvements. Yes, and so one work that I would like to very quickly touch upon is there are many other sources of side information, and I didn't talk about some of them that we worked long ago, like Word2Vec or eye gaze data and things like that, which are all very interesting. But this one was a bit surprising to me. The fact that DNA as side information actually also works quite well for a zero-shot learning task. So what we did here is to take, it's not my expertise, but it seems the DNA sequences have well-known regions which correspond to class-specific properties or the properties that are specific to those objects. Of course, this works only for living beings, but we can take these regions of the DNA, we can convert them to some one-hot encoding and use a CNN model to kind of do dimension reduction further, which leads to an embedding space that is also class specific. And we can use those features that we have learned using DNA as a side information for zero-shot learning. And this seems to work quite well, not as well as attributes, but much better than Word2Vec. So as a conclusion for this part, I talked about attributes and natural language, and I said that these are required as sources of side information when labeled training data is not available. This is a means for transferring knowledge from seen to unseen classes if we are tackling the zero-shot learning problem. And also this side information can be used to generate features as a data augmentation mechanism. That works quite well for zero-shot learning as well. So now I would like to talk about maybe the opposite task. If so we would like to do visual recognition. We still have a classification task, but now we would like to generate textual and visual explanations for the predictions. So more precisely, the task is as follows. We have a user that is communicating to a machine. The machine is able to classify objects. So the user might ask any type of question about the object, like what type of bird is this? And the model needs to say it's a cardinal, so the predicted label, and it needs to go further than that and say because it's a red bird with a red beak and a black face. We would like this sentence to be class specific, which means it needs to talk about properties that are important to distinguish this class from others. So not all of the properties. And we would like these sentences to be also image specific. So if a certain body part, even if it is important, doesn't appear in the image, then the model shouldn't talk about it. To improve this image relevance, we could force the model to point to the evidence of these properties. So if the model says red bird, it needs to draw a bounding box around the red bird and so on. Another type of, so this is a factual explanation or a justification. We would also like to, like the model to be able to generate counterfactual explanations or contrastive explanations. So the user might ask, why not a vermilion flycatcher? Now the model needs to think about what a vermilion flycatcher looks like, and then and say which properties of the vermilion flycatcher do not appear in this image. So because it doesn't have black wings in this case. Briefly, how this could be implemented is we can take an image, we extract features from it. We in fact even do the classification, because deep learning models work very well for this kind of tasks. We don't want to lose from accuracy. And in a post hoc manner, we would like to explain why this class is associated with this image. And yeah. So we have the image feature and the class label that comes from the decision maker. And then these are fed as conditioning variables to a language model that learns to generate sentences that we have, like the ones that we have seen before. This red bird has a red beak and a black face. But this language model is not only optimized for fluency, for generating as fluent sentences as possible, but it has an additional loss that ensures class specificity. So if after generating the sentence, if the sentence has enough information to be classified correctly, we keep that sentence, otherwise we sample another sentence. And then to improve image specificity, we take the sentence, we divide it into noun phrases with a part of speech tagger. And then, so there is no learning at this stage. And then we have an explanation grounder. This is a model that is trained on a different data set because we don't have bounding boxes for this image. But this model needs to predict the locations for the noun phrases that the chunker has detected. We can do it for multiple sentences, and then based on the correspondence between a bounding box and the noun phrase and the cumulative score of all the bounding boxes and all the noun phrases, we can decide which sentence has a better score, and that sentence will be the sentence that is presented to the user. So when it comes to generating these sentences, we start with a template, because for this data set, we actually didn't collect explanations. We have descriptions available. So the model has to convert them into explanations, which means we need to make them more class specific. And we have a template. This is a because, so this is the predicted label. The rest of the sentence is generated. This is the model that has the bounding box capability, and this model is an ablation of this model, which doesn't have the bounding boxes. And we can see that we have actually also asked users if they find bounding boxes useful, and it turned out to be significantly more important than not having bounding boxes. And also we saw that the properties that the model mentions are more class specific when we force it to point to the evidence. I mentioned contrastive explanations. So we are able to do that using this model with a bit of manual intervention, where we generate the first sentence, the factual sentence for the image, for this image. And this image is just an image that corresponds to another class that seems to be the closest to the image, to the class of this image. And it's just an example. The model doesn't see this image. What it knows, though, is for that particular class, we have it has access to a list of attributes that are, or noun phrases that are class specific, and it tries to project those attributes onto the original image. And the attribute or the noun phrase that gets the lowest score is assumed to be the counterfactual phrase. So crested ochret is the positive label, and we have the justification sentence, and it is not a red-faced cormorant, the class of this image, because it doesn't have a long flat bill. Apparently, long flat bill is the property that has the lowest score when we want to project it onto this image. We have applied the same language model on video datasets and more real-world scenarios like self-driving vehicles. And we saw that these are videos that are 30 to 40 seconds long. The videos need to be divided into multiple parts, usually approximately 5 parts, and every part gets associated with a sentence because and the criteria for splitting the video is once it marks where the driver changes his or her behavior, and that behavior change is marked and associated with a sentence. And these sentences could be used to train the models. And the decision maker now is a model that predicts the course and the acceleration of the vehicle. Using those as conditioning variables, we generate sentences that look like this. We see that these sentences are indeed class specific and related to the video that they get associated with, and also they are quite they have a very good variation. So the model doesn't always use the same words to describe a certain situation. And another related task to explainability, or textual and visual or multimodal explainability, is visual question answering. So in this case, what we would like to do is, so the task is, we have an image, we have a question that is associated with it, and an answer to that question. Is this a healthy meal for this image? The answer is no. And then the model needs to generate a textual justification and the visual pointing for that. So the justification talks about what are the properties that are visible in the image that makes the answer known. So it's a hot dog with a lot of toppings. And the visual pointing, this is similar to bounding boxes, but instead of having an out-of-the-box bounding box detection model, we just simply overlay the attention. The regions in the image that led most to the classification decision. For an alternative image that gives a different answer, the model talks about the other properties, like the meal is healthy now because of the variety of vegetables, and those are pointed to in the image. So this kind of a framework makes already tries to make the model more introspective than just a justification model. So it makes the model more kind of the decision maker itself needs to generate the explanation instead of using a black box decision maker and a justification that happens on top of it. And to take this one step further, we would like to build a decision maker that is transparent on its own. So, and without losing accuracy. For that, we thought we could design a communication game like this one. Let's say there are two robots that communicate with each other. One of them has some predictions of the kind of classes this image could contain, and but doesn't have access to the image. The other model has access to the image and is able to give directly the class label of that image, but we restrict it. We have a bottleneck there that that we force the red agent not to reveal its first thought, but it can only give an answer to the question that it is being asked. Is it furry? The model says yes, and then this eliminates already two of the classes. Then the remaining classes determine the next question. Does it have whiskers? No, and this is enough. This answer is enough for the first model to predict it's a dog. And this kind of decision-making mechanism that resembles decision trees makes the model much more transparent. Very briefly, how it works: we have two agents, the blue agent and the red agent. The blue agent is a recurrent decision tree. It's an LSTM model with an integrated memory mechanism. The hidden unit activations of the LSTM get fed to an MLP, and that decides on the next question. And the next question is decided based on how well this question, the answer to that question, is going to separate the classes. And then the second agent is an attribute-based learner that takes an image, extracts features from them, and then we have an MLP that predicts all of the possible attributes for that image. But the red agent is not allowed to reveal all of the answers. It can only reveal the answer of the question that it is asked. In this case, the whiskers is no, and that stops the decision-making process because this reveals the fact that the object belongs to a dog class. This kind of a decision-making mechanism could help in situations like this. We have two images that may come from the same class. And so the first question is, does it have white underparts? And both of the images have white underparts, so both of them fall into the same bucket. And then with the progression of the question answering, at the end, we see that at this point, they fall in two different buckets based on the black wings property. So it seems the second image has the black wings and the first one doesn't. So the first one gets classified incorrectly into the blue kingfisher class. And if we look at the image, we can see that maybe the model has given the wrong answer because the black wings weren't visible when the bird is flying. So we can see that this is already a bit more transparent in the decision-making process. And we can also point to some other interesting observations. For example, for this class, the female bird looks like this, and the male bird looks like this. For a field expert, both of these images contain the most common properties. That's why they get classified into the same species. But for a novice user, this image has a black head, and this could be treated as class specific. And it seems like this model gets confused with such a situation as well, and learns that black crown is a class specific property of this object, although it is class specific only for male birds. So we can see where the model has made a mistake in these situations as well. Another interesting task for multimodal explainability is visual entailment. This is an a task that is developed in an NLP. Maybe some of you are even more familiar with this task than me, but what we did was to collect explanations for why the answer is decided in this way. So the task is, we have an hypothesis, the people are flying kites at the beach, and we have an image. Now we need to decide, the model needs to decide whether this sentence and this image are corresponding to each other. The answer could be contradiction. So in this case, these two things are contradicting. Otherwise, it could be entailment. So the sentence and the image are in line with each other, or it could be neutral. The sentence or the image doesn't have enough information for the sentence to be correct. And we see that compared to the ground truth explanation, the generated explanation is already quite good. We use a answer conditioning, explanation generation, or language or sentence generation model that is not only that's not an LSTM, but it uses transformers. So it's just a much improved version of what we were using before. And then I talked also about visual explanations in the form of bounding boxes and also attention maps. And also in the language side, I talked about contrastive explanations, and now comes the contrastive explanation on the attention side, so the visual side. Ideally, what we would like to do is what in my opinion constitutes an explanation, a visual explanation, is not necessarily an attention map that spans the entire the entirety of the object. So we can't, for example, use object localization to evaluate whether the explanation is correct or not, because for let's say for fine-grained data sets, the model needs to explain why this object is the class A and not class B. So, but both of the classes are birds, so the bounding box is going to be overlaid in the exact same location in both cases. So we would like the model to eliminate all the attention that doesn't fall on the class discriminative properties of this image. So this work was aiming at that. And finally, I find, so here we haven't made a connection with explainability yet, but it's important to also think about uncertainty and perhaps use it as a refinement procedure, using uncertainty as a refinement procedure for generating better images. So what we did here was an unpaired image-to-image translation, and we would like it to be a robust framework, and the robustness is achieved by uncertainty. Specifically, the regions that have the least confidence for generating a certain image are focused on more strongly, and those regions are refined. But the other regions, the regions that don't have uncertainty, are left as is, and this leads to a model that converges much faster. As conclusions, I talked about attributes and natural language as explanations, and I mentioned that if we are talking about explainability, we need to generate sentences that are class-specific, image-relevant, that are groundable. So the evidence of the prediction needs to be in both in the image and in the sentence, and they need to be contrastive. So we need to be able to say why this sentence, why this class is not associated with this image and the other one. And language can also be used to constrain the system for improved interpretability, the way we did it with the decision trees paper. So if we have some form of filtering mechanism, restriction to the model, then we may be able to achieve interpretability. And also, I didn't have the chance to talk about this, but I think it's important the language can be used to understand the conceptual understanding of the model or the user. What I mean by that is when we generate an explanation, we need to consider the needs of the user. So, or the capabilities of the user in terms of understanding. When we talk to a 5-year-old versus a grad student, we use different words when we want to explain a concept. And in the end, the artificial agents that generate explanations also need to have that ability, in my opinion. As a summary, I talked about attributes and language-based explanations and the zero-shot learning problem. And I mentioned that vision and language complement each other for various tasks. And also, I took users' perspective as the criteria for developing better explainable deep models. And this brings me to the last part of the talk, where I would like to think about what would an ideal system look like that we could use in our daily lives. So let's say for the autonomous driving task, we are sitting in a self-driving car and the car is moving forward. Nothing exciting is happening. So the user might decide to fall asleep, and the next moment they wake up, the car might be stopped. And then the user could ask questions like, what happened? And we would expect the AI system to say, I was driving down an empty road, I decided to slow down as a ball appeared on the right, maybe even show when that happened, replay the scene. And I saw a child running towards the wall, so I decided to stop. This kind of an argument would make the model much more user-friendly and much trustworthy. But of course, language comes with a lot of challenges, like the user might ask, what would have happened if you did not stop? Then the model would say, if there was an impact, the child would have gotten hurt. And although this looks like a very simple sentence, generating this is very, very difficult, because the model needs to think about alternative scenarios, maybe handle uncertainties, and maybe even also have some form of empathy in the way it chooses the words. So the stationary object is a child, and if I hit the child wouldn't be broken, but they would be hurt. So the language has such intricacies that we use in our daily lives without really thinking about them. But if we want to design a model, it's going to lead to additional challenges. This is the end of my talk. Thank you for your attention. And if you have questions, I would be happy to answer them.
Yeah, so first of all, thank you very much for this very exciting talk. We saw a number of very nice applications here, and I'm sure there will be many questions. I can already see several questions being asked in the Q&A. So for the others in the audience,